This is lesson 9.7, Factor Special Products. You should be on page 600. Now, you've learned already in this chapter how to factor trinomials of this form when A is 1 or when A is something other than 1. Now, to do that, it takes a little work. If A is 1, you got to figure out what times what C and adds it to B. If A is something other than 1, then you have to use the Brooklyn method. Now, the word special means shortcuts again. So instead of doing the work, if we can picture or if we see these shortcuts, we can do the factoring in a lot quicker manner. Now, there's two special cases today that we're going to cover. The first special case, the first special product, you studied in lesson 9.3 to factor polynomials, such as the difference of two squares. Now, the difference of two squares working backwards, you learned in 9.3 if you had the sum and difference of the same binomial, there was a two-step shortcut. You could take x times x and negative 3 times 3, and you got x squared minus 9. Now, I want you to notice this is the difference of two squares, x squared and 3 squared. So this is a shortcut. If you see the difference of two squares, you can immediately take those squares, in this case it would be x and 3, and just write it out as x minus 3x plus 3, and you're done factoring. You wouldn't have to use the Brooklyn method, or you wouldn't have to figure out what times what's negative 9 and adds up to 0 in the middle. There's a shortcut. It's the difference of two squares. Now remember, difference means subtract, and squares means perfect squares. Squares means something to the second power. So here would be an example here. 4x squared minus 9, as soon as I look at this, I see it's a special case. It's the subtraction of two perfect squares. Because 2x, if I square it, gets me 4x squared, and 3 squared gives me 9. So I immediately know the proper factoring for this would be just 2x minus 3 and a 2x plus 3. It's that sum and difference pattern that we worked on earlier in the chapter. Okay? Let's try a few of those. So if I look here, y squared minus 16, that's the subtraction of two perfect squares. Y is being squared and 4 is being squared. So as soon as I see the difference of two squares, I know it's a sum and difference pattern. I can write y plus 4, y minus 4. Or in the next sample, I see the difference of two squares. I see 5m being squared, and I see 6 being squared, because 6 squared is 36. So the proper factoring would be 5m plus 6, 5m minus 6. And the next question, or the next sample, x squared minus 49y squared. X is being squared, and 7y is being squared, because 7y squared is 49y squared. So as soon as I see x and 7y, I can write x plus 7y, x minus 7y. Every one of these are a difference, a subtraction, difference is subtraction, of two perfect squares. Sometimes you might have to factor first. Remember, the first step of factoring is, do you have a greatest common factor? So when you see this example, do you notice how I can divide 8 and 18 by 2? So I factor out the 2. Let me circle that. We factored out the 2. Do you notice how what's left are two perfect squares being subtracted? 2 squared is 4, and 3n squared is 9n squared. Can you see right here? Let me highlight it. Can you see how I have the difference of squares? Well, then that's easy. I would have 2 minus 3n and 2 plus 3n, and I'd have that 2 factored out front. Okay? So, I want you to try. Pause the video, factor the polynomial 4y squared minus 64. Okay, I'm back, and the first step, I have a common factor. I can divide both of those by 4, so you can see I undistributed the 4. Let me highlight that. It's right here. And then, do you notice y squared is a perfect square, so is 16. 16 is 4 squared. Can you see here I have the difference, the subtraction of perfect squares? Whenever you have a difference of two squares, there's a shortcut. You can just take each of those, y and 4, and do y minus 4, y plus 4, and the 4 that I factored out in front is still there. So this should be a nice, simple shortcut, but here's the thing. You got to notice it. You got to notice that you have a subtraction of perfect squares. Okay? There is a second shortcut we're going to learn today. It's called the perfect square trinomial pattern. The pattern for finding the square of a binomial. Now let me underline that, because we learned about squares of binomials again back in lesson 9.3. The pattern for finding the square of the binomial gives you the pattern for factoring trinomials of the form. Remember, back in 9.3, we would square the first term, square the last term, and then multiply those together and double to get the middle. Does that ring a bell from 9.3, a perfect square trinomial? That was called a binomial squared. It creates a perfect square trinomial. So for example, if I had x plus 2y squared back in lesson 9.3, I would square the x, I would square the 2y, which would be 4y squared. I'd multiply these two together. X times 2y is 2xy, and I would double it. Okay? Now, this is called a perfect square trinomial. So if I see this and I'm asked to factor it, do you notice how the first term is a perfect square? It's x being squared. The last term is a perfect square. It's 2y being squared. And if I take 2y and x and multiply and I double, you notice how I get the middle amount. Well, whenever that's the case, you have what's called a perfect square trinomial, and all you have to do to factor it is just write the first term x, write the last term 2y, and then square it. X plus 2y is squared. That would be the proper factoring. I don't have to use the Brooklyn method or figure out what times what's 4 and adds up to 4 in the middle. So, for example, when we look here at this problem, x squared plus 6x plus 9. Now do you notice? X squared is a perfect square. It's x being squared. 9 is a perfect square. It's 3 being squared. And if I take 3 and x and I multiply that, I get 3x. If I double it, there's my 6x in the middle. So the proper factoring for this would be x plus 3. There's x and 3 squared. That's the proper factoring. Or this problem. X is being squared, that's a perfect square. 5 is being squared, 5 squared 25, and if I take 5 times x and I double it, there's my 10x. Okay, now they have a subtraction here, so the proper factoring would be x minus 5. There's my x and 5, x minus 5 squared. Okay? That's called a perfect square trinomial. It's the complete reverse of the square of a binomial pattern you learned earlier in the chapter. Okay, let's try some. N squared minus 12n plus 36. Well, do you notice n squared is a perfect square, it's n being squared. 36 is a perfect square, it's 6 being squared, and if I take 6n and double, I get 12n. Okay, so from there, I would have n minus 6 being squared. Okay, n minus 6 squared is the proper factoring for this. Now, if you don't know the shortcut, it doesn't mean you're not going to get the answer right. What it means is you're going to have to just go and figure out what times what's 36 and adds up to negative 12 in the middle, and if it takes you 2 or 3 minutes to figure out the combination, that's what you got. So it's nice to know the shortcut. Okay? Same thing in part B. Okay? You notice that's a perfect square. It's 3x being squared. 3x times itself is 9x squared. And you notice 4 is a perfect square. 2 squared is 4. And if I take 3x times 2, I get 6x, and if I double that, I get 12x. So I got to take 3x and 2. I got to subtract, because there was a minus in the middle, and square it. There's my factoring. Okay, now, if you don't know that, if you can't see the shortcut, it doesn't mean you won't get the answer, but you're going to have to do the Brooklyn method then. You're going to have to take 9 times 4 is 36, and take x squared minus 12x plus 36, you're going to have to figure out what times what's 36 and adds up to negative 12. And then after that, remember, since you multiplied by 9, you'd have to divide by 9. So it could take you more time if you don't see the shortcut. Okay? Same thing here. This is a perfect square trinomial. If I take 2s and square it, I get 4s squared. If I take t and square it, I get t squared. If I take 2s and t and multiply, 2st, if I double that amount, there's my 4st in the middle. So the proper factoring should be 2s plus t, and I'm squaring it. Okay? Let's look at one more. Factor the perfect square trinomial. All right? So for this problem, so remember, when you factor a question, you always want to try to find the greatest common factor first. You notice I do not want the lead coefficient negative, never want that. I can divide all of these by 3. So can you see they're factoring out the negative 3, and when you divide each of these by negative 3, you get y squared minus 12y plus 36. Now, this is a perfect square trinomial. In fact, we've already done one just like it. Y is being squared, 6 squared is 36, and if I take y and 6 and multiply those, I get 6y. If I double that, there's my 12y in the middle. So there's my factoring. It'd be the negative 3 out front with the y minus 6 being squared, which you see there. Okay? Let's have you pause the video, and let's have you try these 3. Okay, so the first one, this is a perfect square trinomial. H is being squared, 2 squared is 4, and if I take 2 and h and double, I get 4h in the middle. This is just h plus 2 squared. Okay? Here, you got to start off by dividing everything by 2 because I have a common factor. Now when you divide everything by 2, you notice y is being squared, 5 is being squared, and 5y doubles 10y. The proper factoring would be y minus 5 squared with the 2 factored out front. And then here, the next one is the same thing. We have to divide everything by 3, factor out that 3. I have a perfect square here, x. Y is being squared, and if I multiply x, y, and double, I get the middle. So the proper factoring is 3 with the x plus y being squared. Now again, the better you are at your mental math, the quicker this is going to go. If you have to think about, you know, if you're not sure that 25 is a perfect square, and you have to stop and think all the time, it's just going to slow the process down. So the better you are at mental math, the more you're going to reward yourself here. Let's talk about solving a polynomial equation. Now again, when you have second degree, the first step, get everything on one side, 0 on the other. Now you notice the problem is already set up that way. Okay? Next step, I don't want these fractions in the problem, so you notice that I have a common denominator of 9. If 3 goes into 9 3 times. So if I multiply everything by 9, let me write that out. If I multiply by 9 here, and I multiply by 9 here, 0 times 9 is 0. I'll distribute, and I'll have 9x squared. 9 times 2/3 is 6x, and 9 times a ninth is 1. Now, I'm going to say, why did you do that? I got rid of all the fractions. Should be easier to work with. Now, look carefully. You notice I'm going to put PST next to this. This is a perfect square trinomial. Do you notice how 3x is being squared to get 9x squared? 1 is being squared to get 1, and if I take 3x times 1, that's 3x, and if I double it, there's my 6x in the middle. This is a perfect square trinomial pattern. So the proper factoring is 3x plus 1 squared equals 0, which you see here. Okay, let me solve that. I need this to work out to 0. So 3x plus 1 would have to be 0. Take away the 1, and then divide by the 3, and that's why you're seeing x is negative 1/3 according to the book. That's the solution to the problem. Last question. You got to be able to use the vertical motion model and solve using these techniques for that model now. So you notice we have a window washer drops a wet sponge from a height of 64 feet. So there's the starting height at 64. Let me write that down. S equals 64. After how many seconds does the sponge land on the ground? Well, it lands on the ground when h is 0. Use the vertical motion model. The sponge was dropped, so it had no initial velocity, which means v is 0. So think about that. When the sponge first leaves the person's hand, it had no velocity. It was being held. It wasn't thrown. It was just dropped, let go. So it had no velocity to start. So that's why you notice they're plugging in 0 for h, they're plugging in 0 for v, and they're plugging in 64 for s, and they want me to solve for t. So let me write this out. I have 0 equals negative 16 t squared plus 64. Okay. I never want my lead coefficient negative, and I always want to find a common factor. Well, let's factor out the negative, and I can divide both those by 16. So when I do, I get t squared minus 4 left. Now, do you notice from earlier in the video, this is a difference of perfect squares. I have t being squared, and I have 2 being squared. So the proper factoring here would just be t minus 2, t plus 2. And now I want to solve. Negative 16 times this is 0. Okay, I need one of these two to equal 0. Well, for t minus 2 to equal 0, t would be a 2. For t plus 2 to equal 0, t would be negative 2. Now I can't go backward in time, so I'll throw that one out. T would be 2 is the answer to the problem. I think I'm going to pause the video there. If you have questions, make sure you ask during class.